Hello and welcome to this video on extended set difference. So it's a continuation of videos that I did before on the Minkowski sum and the Hausdorff distance. And as before, we start from the vector space Rd with the Euclidean distance, and this script K is the set of all compact and convex subsets in Rd. Okay, so that's our starting point, and we reviewed these concepts before. Okay, so going back to the Minkowski sum, okay, we had a definition of the summation, and we are interested in thinking about an operation which is a difference, a subtraction. Okay, and the question, how do we define such a operation? Just to remind you that if we have a set A, okay, which is compact and convex, and we perform the Minkowski sum of the set A with the negation of A, which is taking all the elements in A and multiplying them by -1, that is not equal to the set with just a zero vector. That's not a good subtraction operation. Okay. So what can we do in terms of subtraction? So here is the first solution that was suggested by Okuhara. Okay. And this is already in 1967, okay, a while ago. And he says the following. Think about numbers, okay, or vectors in Rd. Okay, A minus B equal to C is equivalent to saying that A is equal to B plus C. And the plus is an operation that we know how to do in sets. So the Okuhara difference of a set A minus a set B, and we will put here a letter H to remind us that it's a Okuhara difference, is going to be equal to a set C, such that, okay, A is equal to B Minkowski sum, well defined, C. Okay. Now the question is this a good definition in the sense that does it always exist? Okay. And the answer is no. No, not necessarily you can find a set C such that you will add it to B and it will be equal to A. There are two problems here. One is shape, and the other one is size. And here is what I mean by that. Okay, so suppose B is a bigger set. Okay, I'm talking about size first. B is a bigger set. If you add something to it, it's not going to be ever equal to A. So that's one problem. The second problem, or the first that I wrote here, is a shape. If B is a square and A is a circle, there is nothing that you can add to the square that will make it a circle. Okay. But let's think about something simple. Does it exist at least in R1? Okay, so let's look at R1. In R1, this K, script K, is the set of all closed interval with two finite endpoints. So if I take two sets, okay, in R1, which are compact and convex, two intervals, is this operation here always defined. And in R1, okay, A minus Okuhara minus B exists, okay, if and only if there exists a number C, or a vector C, it's a number in R, such that, okay, if you add to B this number turned into a set, okay, so it's going to be a Minkowski, it will be included inside A. Okay, if we can shift B, left or right, doesn't matter, such that it will enter and be included in A, then the Okuhara difference is defined. If this is not true, the Okuhara difference is not defined. Why am I talking about R1? Because in R1, the shape is not a problem. All the compact convex sets are intervals, they are of the same shape. It's just the size. Okay, so it still does not exist even in R1. Then came another suggestion, Stefanini. And this is in 2010. Okay. And he says that A minus B as numbers equal to C is indeed equivalent, like Ukuara said, to A equal to B plus C, and also equivalent, okay, to A plus the negation of C equal to B. Okay? So Ukuara, the Stefanini is calling it generalized Ukuara. Okay, so he says A minus B generalized Ukuara is equal to C, okay, such that C is equal to the A minus Ukuara, the original one, B, if exists. Okay. If not, okay, if not, then C is such that A plus, and again that's the Minkowski plus, minus C is equal to B. Okay? Then, okay, so the C is this set that satisfies this. Now, in R1, this finally exists, because in R1, it's either there exists a number C such that B plus that number comes into A, or there exists a C such that if you add it to A, it will be included in B, one of the two. Okay, or they will exactly overlap, which is okay as well. Okay, so the Stefanini generalized Ukuara difference exists in R1. Okay. Now, again, the reason why the Stefanini concept exists is because there is no shape issue. Okay, they are all of the same shape, and he solves the size issue by saying either we can take B into A or A into B, and that will be how we define the difference. Okay. Now, moving to arc D. Okay, for D bigger than or equal to 2, okay, more than one dimension. The two concepts, and let's talk about the more general one, a generalized, is not necessarily exist. Okay, so it does not exist for all A and B in this, even if we look at just compact and convex. Okay, so here comes the new definition that we call the extended set difference. And this is based on a paper, and I'll put a link in the comments below, which I wrote with a graduate student in our department, Behrooz. And we define the extended set difference in the following way. Okay, so we say that A minus, and we put here a lowercase e for extended B. Okay, so again, for two sets in K sub KC, okay, we will define it to be the arg infimum, okay, of over all the x's in this KC. Okay, so we are looking for an x which will be called the difference, such that the distance, the Hausdorff distance between A and B Minkowski sum x, okay, is minimized. Okay, all the minimizers here. Okay, so what is the concept here? Again, if we write all these equivalences here, we can write another equivalence which is true in RD, which says the following, that A minus B is equal to C if and only if, okay, the distance, the regular distance, this Euclidean distance, okay, the Euclidean distance between A and B plus C, okay, this Euclidean norm, Euclidean distance, is equal to 0. Okay? So in Rd, if you look at vectors in Rd, you can find always C, because you can define C to be equal to A minus B. That's always defined. And that will also give you, of course, this distance equal to 0. And it will be unique. Okay? So this is this definition here, okay, this definition here that is new in our paper, says the following. Instead of trying to pin down A exactly, find a set X that brings you, when you add it to B, the closest possible to A. And here is what will happen. Okay, so if we are trying to subtract a circle minus a square, okay, we will find something to add to the square, okay, that will bring it into the circle or overlapping the circle in a way that will minimize the Hausdorff distance between the new B plus X and A. Okay, so the first thing that I want to say, or the last thing in this video here, is the following 2 points. Okay, first of all, existence. Okay, will there be an X here that will, okay, is it an empty set or not? So existence is proved in the paper, and yes, this set of minimizers is non-empty. The second result, or the second observation there in terms of uniqueness, no, not necessarily. There can be more than one minimizer. Let me give you a very simple example that can be used for counterexamples for certain claims that are not necessarily true. If, again, think about Rd, which is R squared. Okay, if the set A is just this segment, okay, and it can go from -1, 0 to, sorry, from 0, -1 to 0, 1, and this is the set A, okay? And the set B is just another segment which is exactly perpendicular to it, and that goes from -1, 0 to 1, 0, okay? And that will be the set B. Okay, let's call it B. Okay, so A minus B extended. Okay, the Ukwara and the general Ukwara do not exist here, but A extended difference B. Okay, there can be more than one solutions here, because the distance between them, the Hausdorff distance, is equal to 1. Okay, it's the farthest point in A from B, or the B from A. It's going to be 1. So what can I add to A that will make it smaller? I can't make it smaller, actually. But I can add to B a certain segment that will turn this segment, or a certain set, that will turn it into a rectangle like this, which will still be of distance 1 from, or the Hausdorff distance will be 1 from A. And I can make it, add it a little bit more, that will turn the B plus X to be this rectangle, still equal, the distance equal to 1. So there can be more than one X that I can add to B, such that the distance would be the minimum, which is still going to be equal to 1. Okay, so uniqueness is not true, or not proven, cannot be proven in this definition. In the next video, I will add some more properties and show under what conditions or what changes to this definition can be made such that uniqueness will be achieved.